Welcome everyone. My name is Gihan Mudalige from the Department of Aeronautics at Imperial College London, and this is the new episode of the Turbulence at the Exascale podcast. So the aim of the podcast is to gather the view of the community regarding exascale computing for turbulence and what are the challenges and opportunities about exascale computing for turbulence research. So the UK has launched recently a program called ExCALIBUR, which will run until 2025. It is led by the Met Office, the UK Atomic Energy Authority, and the UK Research and Innovation. And the aim of ExCALIBUR is to deliver research and innovation algorithm developments to harness the power of exascale computing. So the first phase of the project was to design working groups to focus on different software strategy to investigate a wide range of problems using exascale computing. So I lead the working group on turbulence, and this podcast will help us to better understand how we can efficiently use exascale computing to advance our knowledge of turbulence. The working group I led is strongly connected with the UK Turbulence Consortium, which is a group of academics and researchers who are using supercomputing facilities in the UK to advance our knowledge of turbulent flow. So today, our podcast guest is Gihan Mudalige, who is an associate professor and Royal Society Industry Fellow in the Department of Computer Science at the University of Warwick. And his research focuses on the development of high-performance computing software libraries through the domain-specific high-level abstraction frameworks. Is also involved in two ExCALIBUR working groups. So it is a great pleasure to have him today to talk about his research. So good morning, Gihan.
Morning, Silva.
I'm going to ask you, first question is, can you tell us more about yourself, where you are from, what you have studied and where, and any previous position?
So I think you summed up quite well with that introduction. So I'm a associate professor at the University of Warwick's Computer Science Department, and I currently lead the High Performance and Scientific Computing Research Group there. I'm also a Royal Society Industry Fellow, and that entails working with Rolls-Royce on a research project aimed at developing massively parallel CFD simulation software targeting exascale supercomputers. And I'm originally from Sri Lanka, having done up to my A-levels there, and then coming to the UK to follow a degree in computer systems engineering at Warwick, and then staying on to do a PhD at Warwick. And after completing my PhD, I worked at Oxford for about 6 years as a senior researcher and a associate research associate and a senior researcher, and then joined Warwick back again in 2016. So that's sort of my journey around. Yeah.
Fantastic. So my first question is, what's the best thing about your job and about working at Warwick in your department in computer science?
Warwick is a very open and very friendly campus. I should say that. And in terms of the work itself, I think it's the hands-on research and development work that is the exciting part. So there's usually no dull day at the office, if you know what I mean. You're always pushed to think deeply and reason about these big, challenging problems, and that conversation you have with yourself, with your team, is something I really enjoy. And as part of this, a very exciting part is working with the collaboration that brings in. It's an inherent part of, I think, academic work, and that's the case with the work that I do as well. You get to work with some of the smartest minds in the world, and work with some of the most innovative industrial and commercial companies, large and small, and then getting all of that together to contribute to advance the state of the art is what is really exciting.
Fantastic. So can you tell us more about how you got interested in computer science and in high performance computing?
Oh, okay. So I did A levels at maths, as many of the people working in this field would have done. At that time, I was introduced to continuous mathematics, basically calculus, if you will. And I was really interested in this area. But then a number of circumstances, maybe the educational system coming from Sri Lanka, it basically led me to work with computers and sort of look at the hardware software interface between, in computing. So that led to my degree at Warwick, and then it's only really I learned about HPC when I started doing maybe the final years of my degree and then getting into a PhD, and then everything really clicked, because HPC straddles this domain, several domains. It's very interdisciplinary. At one side you've got computer science, parallel computing, algorithms, complexity of algorithms, and then architectures, memory systems, processors, caches, and so on. And then you also have mathematics, so numerical methods, which is a vast area of its own. All of those is covered by HPC in a very deep way, although it's interdisciplinary, holding on to all of these areas. You get to learn a lot about, in deeper. So I think HPC really clicked, or makes me really motivated to work in that area. Yeah, so that's what that keeps me going, I suppose.
Fantastic, thank you very much. So over the years, you have been working on these amazing libraries called OPS and OP2. And this is really at the core of some of the ExCALIBUR working groups. So can you tell us more about those libraries, how they are working, what are they doing, how they are doing it, and well, everything we need to know about them.
Okay, so the project started about 10 years ago. I'll go into a bit of detail about history later. But OP2 and OPS, which is the two libraries I work on, are what we call embedded domain-specific languages. Now, domain-specific means that they narrow the focus of the language and target solving problems for a specific domain. Now, this is as opposed to general purpose programming languages such as C, C++, or Fortran that can be used to write solutions for any computable problem. Now, for this end, OP2 and OPS then provides a domain-specific API, which can be used by an application developer, let's say scientists, engineers, physicists, to describe or specify at a higher level the problem to be solved without detailing how it should be implemented on parallel hardware. And so the implementation is then left to a lower level, which is provided by these libraries, where the specification, the API specification, we have a way to automatically translate it to a concrete parallel implementations. And so there's a separation of concerns that enables applying the best optimizations to gain near optimal performance on each platform. So for example, take the domain of unstructured mesh, which is the domain of OP2, and we see that these keep on occurring in areas such as CFD, computational electromagnetics, and so on. The key motif or computation communication pattern, as I would like to say, is the indirect increments of values held on a mesh element, elements of a mesh, right? So there's an unstructured mesh there. And the key problem here is then how to handle these indirect increments, because that leads to data races when you're parallelizing an iteration over this mesh. Now, experts, parallel computing experts, have been developing such codes for years and know how to best implement them on different architectures and different memory hierarchies, and so on. But the problem is that every time you get a new piece of hardware or different way to program, you do not want to be rewriting your code every time to target a different hardware architecture. And this is going to be basically impossible to do for a massive code base. And so what we do with OP2 and OPS is to provide a way for the users to automatically generate these expert implementations for different hardware, looking at the problem description that's written at a higher level, so that specification written using this API. And so the science source remains unchanged without needing to reprogram it for different hardware. And so this also enables us to easily add new parallelizations or new hardware or program new hardware, ways to program new hardware as they appear. And so that means the code written at a high level can be translated to utilize these new hardware with the confidence that we are generating the best possible optimizations for that target platform. And so, we say that these are embedded because we made a conscious decision to embed this API in a general purpose language, so C and Fortran. And so that means we are not introducing a whole new programming languages, but simply an API that looks like a classical library. And this also enables us, a great benefit is that we can leverage existing compilers, tool chains, debuggers, profilers, and various things that the general purpose language itself support. So we don't have to, reinvent these things again for a completely different language. And also this enables the user to easily pick up, because it's basically general purpose language that people know. And all you need to learn about is the API, which looks like a classical language, a classical library.
Mm-hmm.
So yeah, so the idea is simple. I suppose that's why we are going on after 10 years or so. So over the years when we started this, so the project was this abstraction project. Ideas started off at Oxford when I was with Professor Mike Giles there, and also the project was led by Professor Paul Kelly at Imperial, and we were doing OP2 at that time. And then now these days it's led by myself and my colleague at Hungary at PPCU, István Reguli, and we maintain and develop these for upcoming hardware and now in this ExCALIBUR project as well. So yeah, so that's I hope that covers everything. I mean, OP2 and OPS is not alone in this respect. There's a lot of traction in using these ideas, this strategy of developing code. There's a lot of frameworks such as PyFR, then DeVito from Imperial itself, Phoenix, for example, and then even loop level abstractions such as Kokos and Raja, which is coming from the DOE labs, have this idea of abstracting things a little bit higher than general purpose languages, simply because it's going to be impossible to use a general purpose language to target all this hardware. And there's different levels of abstraction. You can go even higher with something like OpenSBLI, which I'm sure you're familiar with, where you can basically write mathematical equations and then have multiple layers of code generation that would then generate OPS, and then OPS generates the hardware executable, parallel executable.
Fantastic. Thank you very much. It was very clear description. I just wanted to ask you a curiosity, what are the latest addition or the latest functionalities to OPS and OP2? So basically, what are you working on at the moment?
Right. So Yeah, so we have an experimental. So some of the things we always want to keep on adding new parallelizations or be able to target upcoming hardware. So we have been doing a lot of work on targeting ARM hardware these days. We've got access to the Japanese supercomputer Fugaku, which has ARM processor. So my colleague Ishtvan is currently aware. As we talk, he's working on this machine, and there's been a SYCL or let's say people heard of One API from Intel, which is based on this SYCL standard, which is an OpenCL, much better than OpenCL, I would say. We've got code generators spitting out code, SYCL code, for both OP2 and I think experimentally OPS as well. So that's in terms of new hardware and software. Also, I have a strand of work which is really experimental, trying to do this for FPGAs, but that's nowhere near complete. I mean, I don't come from an FPGA background. I mean, I collaborate with researchers at engineering department in Warwick. The problem is that we don't know what is the best way to get best performance on FPGAs, because they are very limited in the hardware capabilities. And so there is a very experimental strand going on, trying to do whether there's some class of applications, maybe small meshes, single precision, that can challenge the dominance of, say, GPUs, which we see as the best architectures currently for structured mesh, for example.
Fantastic. So, I mean, I probably already know the answer, but I'm going to ask you anyway. So, so we are going to have access to Exascale supercomputers very soon, within a year or two, or a little bit more, maybe in the UK. So do you think that library like OPS and OP2 is the way forward to make the best use of Exascale computer?
So yeah, definitely. So I don't think there is still a consensus of what an exascale machine would look like. So if you look at the large DOE machines and their purchases, they still don't know, and they're looking at a range of options, and you cannot really. I don't think you can fix your code base into just one way. Let's say writing it for CPUs. And that's characteristics of the era we live in. We are at we are trying to milk out as much performance from the end of Moore's law, if you will, although it's still going. CMOS is it's basically at the end of its life, and so that has led to the software side and also the hardware side trying to innovate in a way that we have not seen before. It's a golden age of parallel programming research, I would think. And so you cannot be fixed into one language, one way of programming. And so because the way we are doing it, it's simple. I mean, everybody can see it. It's not a deep abstraction where the layers of software is not deep. There's not many layers. If you look at the code base itself, it's not big. It's very manageable, the OPS, OP2 code bases. And I think this gives us a very agile way to program. By agile, I mean, we have always had this problem of you want open standards to capture all these different architectures and be able to program them, but they are a bit slow to catch up. And we see this OpenMP, when OpenMP 4 and OpenMP 4.5 and now 5 comes up, it was slow to catch up with GPUs and latest hardware. And then we see the same with SYCL, something like SYCL. But then you get proprietary solutions that gets you locked into their hardware. and we can't be locked in. And so the way we do it with OPS and OP2, I think gives us this agility to change and do it ourselves without waiting for anyone else to do it. But that doesn't mean we are throwing away open standards or proprietary solutions. We actually incorporate it and try to get the best of what's out there.
Great. Fantastic. Thank you very much. I know that you also were in a project called Asimov, which is a strategic partnership with Rolls-Royce. So can you tell us a bit more about this Asimov project?
Yes, so Asimov project is basically aimed to get gas turbine engines virtually certified. So virtual certification of gas turbine engines, while also developing the next generation simulations to get to the next level of what Rolls-Royce would want to get their solution or simulations done. So that what that means is that you want to be able to fully certify the design of a gas turbine engine for their aircrafts. And what we want to do with the Asimov is to get this at a very high fidelity that has not been attempted in a simulation. And so the project is going to run for 5 years, involves universities, Warwick, Bristol, Cambridge, Oxford, and Edinburgh, and Edinburgh leads this. And so the time to solution is a main challenge that we at the strand of work that Warwick is working on. And the key challenge is well, so from what we've heard, is that we need about roughly speaking 7-fold increase in time to get a result out of a simulation. So this is the CFD code base, as well as the CFD combining with other components, say combustion and FEM and so on. So there's this idea of coupled simulations working together to in their workload. So that's the strand I lead, where I try to modernize their CFD code base for these upcoming massively parallel systems, because without these massively parallel architectures, utilizing them, you cannot really expect to get the speed ups there that Rolls-Royce would want to achieve. And so, we are applying OP2 in this project for their code base. So people might have heard their code, CFD code called Hydra. So so actually we've had now converted it and we have a, experimental results going on for Hydra. So now it's a matter of combining that CFD bit with the other coupled simulations. And then there's a huge problem of what's the best configuration to run. The load balancing and the scaling is really difficult to understand by just running it, because these simulations take such a long time. And so another strand that Warwick leads is performance modeling. So Professor Stephen Jarvis, who actually led the group before I took over, does simulation performance modeling, and so we are developing mini apps to inform us and understand this configuration and the problem of how best to lay it out on a massive machine. So that's the two things that we do, and then the other partners are working on the other challenges. So combustion, encryption to run on the cloud. So there's a big push for using cloud resources, because it's going to be easy to farm out your HPC work. But the problem has been, of course, because codes are restricted, proprietary, and so they need to be able to be secure. And so that's another element that Asimov will try to implement for the Rolls-Royce codes.
Wow.
Yeah, so that's what we do in this project.
Great, fantastic. I wanted to ask you, if there is one thing that you can change in high performance computing, what would it be?
Ooh, so there are a couple of things, but I think one of the main things would be what you say, the emphasis on hardware, right? So I think the stakeholders of HPC, government, industry, treats the development of software or software that enables parallelization simulations to run on HPC systems up until recently, I think, as second-class citizens. I would like that to change. There's been a lot of emphasis on hardware innovation, but it's only recently, and for sure, with grants or initiatives such as ExCALIBUR, this is kind of changing. What I would really like is software to be a first-class citizen, because no matter how fantastic your hardware is, if you cannot really drive that hardware with the software, with the level of performance that the hardware is promising, then I mean, it's a shame to have that hardware, right? So I think a lot of users from the domain scientist side, from where we are right now with the problems of developing software for these massively parallel devices, are beginning to understand the importance of it, but there's still an element of a magic bullet or silver bullet coming and solving it for you. And so I think that sort of attitude I would like to change. I think it's changing if you see around, and especially I think UK is catching up with let's say the US and the rest of the world, but I would like to see that more. That's one of the key things. Another thing would be HPC education, parallel computing education, which I think is sort of lagging, and we find it difficult to get students, the next generation, come and help us write these difficult codes and then work on these things. So I think at an undergraduate level, I would like that to see. And maybe also magically overnight, maybe all the old Fortran code goes away. Maybe, but I mean, it's just, sometimes you get, there's still, decades worth of old legacy code, which is part of the problem, or rather something that we have to work with. So maybe that's also in sort of wish list, in this thing that in the wishes I would like to see.
It's a very controversial statement.
Well, no,
to get rid of the Fortran code.
Not get rid of it. I mean, magically have a way of moving that into more performance portable languages. It may be controversial, but if you ask with the parallel computing people developing programming models and programming languages, I mean, look at something like SYCL, for example, that Intel is backing with their one API. How would you go and do Fortran with that? I'm still waiting for that. Maybe, yeah, so OpenMP might be the solution there. And then so we are left with yet more, a diversity of these models again. Fortran is fine, it's fantastic. It's just that, getting that compiler tool chains and all the things that we want to build build good codes is lagging. I think these days C++ is quite up there. It's always on the leading edge. Fortran lags behind. Look at something like LLVM and Clang and Flang. So Clang has been there forever. I'm still not entirely sure what Flang is going to bring. The Fortran front end for the LLVM compiler.
Very good. Yeah. Thank you. Very interesting to have your viewpoint on that. I have a few more questions. So is there any trend in high performance computing that excites you, or that may have you concerned on the opposite?
I think we'll go on like this for some time now. I think the exascale goals will be achieved with this diversity of hardware. I think that they will be pushing through. I don't think the next generation of hardware itself is mature enough to take over from CMOS. Whatever that is going to be, I don't know, quantum computing. I don't know, that might be completely so something that I would know how to comment on. But the next hardware is still not mature enough, and even more not mature enough is the software to program them.
Mm-hmm.
So any new hardware trends would not be able to take up production code bases just yet. And I think we'll achieve exascale with what we have right now, the way we are going. So that would be the trend. I would be looking at how every vendor would try to get their hardware running, hardware usable by these, the codes that's out there. I'll be really keen on keeping an eye on it, because obviously we want to support all of that. Otherwise, I think until exascale comes, this would be the way we are going to be.
Thank you. Quick question before we finish. Do you have any suggestion for guests on this podcast about turbulence and exascale computing?
Right, interesting. So I would always say that someone like Professor Mike Giles might be very insightful, because he's been working in this area for more than 20 years, 30 years. And that he's seen all this trend, and I've seen his talks, and I think he's very good at, coming from a mathematical background, but knowing the whole,
Mm-hmm.
these people who knows all the areas. Anyone who knows Mike would say this. So yeah, so that would be one person. Another one would be one of my colleagues at NAG, Numerical Algorithms Group, Jacques Dutoit.
Yes.
From the conversations I've had with him, he has, I think, a lot of knowledge or insights about how industry works and what NAG does. I think would be a good addition to give an industry perspective on the problems. I mean, there. From the conversation I had with him, he was saying that exascale really, is a bit, away from what his horizons are. But then, you ask him yourself, he'll say that the problems of massively parallel architectures are well and truly in industry, in commercial organizations.
Mm-hmm.
And that I think he would be a good guest as well.
Thank you very much. Well, thank you very much, Gihan, for your time and for your input. It was really, really nice talking to you and to get your opinion, sometimes controversial opinion, I will say.
I hope I haven't.
No. I think it's very interesting. Yeah. We wish you all the best for your future endeavor for OPS, OP2. I mean, we are going to collaborate with each other. We are collaborating with each other. So I'm looking forward to keep working with you.
Okay.
So thank you.
Thank you.
That's it for today. So if you want to learn more about the UK Turbulence Consortium, please go on our website, ukturbulence.co.uk. We also have a Twitter account at UK Turbulence in one word, and all the podcasts are going to be made or are already available on the UK Turbulence Consortium website. So thank you very much, Gihan, and that's all for today.